Hello, my name is Tim Lakeman, and within the next 20 to 25 minutes, you will learn what a Bayesian network is and how you can use it to get more autonomy in your system or robotic platform. Since this video is part of the seminar Planetary Exploration, the use case and focus will be here on planetary rovers. Therefore, I'd like to give an introduction into onboard autonomy. Thus, we know exactly where the classification with Bayesian networks is done in an autonomous system. As a motivation, I'd like to show you a press announcement from NASA. So the SuperCam of the Perseverance rover, which is the current rover of the NASA on Mars, used the Aegis system for the first time. Aegis stands for Autonomous Exploration for gathering increased science. So an artificial intelligence which uses camera images for detecting and classifying rocks autonomously. This press announcement is from the May 31st. Thus you can see that classification with belief nets is done nowadays on Mars already. Within the planetary exploration context, the interest in onboard autonomy can be relatively easy derived since the round-trip times between the rover and the ground station are high. Also, we've got a limited downlink, and therefore the transmission of raw data should be avoided. So one could classify onboard the rover autonomously and then discard the raw data in an autonomous fashion. That would reduce the data transfer, and also the data analysis on the ground station would be less. So if we would have a system which can operate autonomously, this would reduce a lot of overhead regarding communication and therefore cost reduction. Thus, we've got several requirements for our autonomous system. I want to show you here on this slide what are the tasks we are going to solve within this talk in the next few minutes. So we want to characterize rocks, minerals and soils in an autonomous fashion. We want that the rover drives autonomously to the region of interest. Therefore, the probability should be reduced that we have false positive events. For example, if the rover would classify in an image a cavity as a rock and therefore as a region of interest, and the rover would fall into the cavity, the mission would be over. Therefore, this is a really important point. Also, a knowledge base with about 700 rocks and minerals should be built beforehand. Since this is not a geological course, we won't consider this database in detail. Also, the autonomous navigation would be a chapter on its own. Therefore, we will focus in the autonomy for scientific events like rock classification. Or in one sentence, one wants to maximize the scientific productivity while minimizing the interactions to the ground station. However, let's try to solve these given tasks. For that, I would like to start with the definition, since from this definition one can derive the two main parts of this talk. So, science-driven autonomy involves automating the detection of scientific events and their classification on board the rover. So, the first part is the automating the detection of scientific events. And the second part is the classification on board the rover. So let's take a look at the automating part. Within the chapter in the book, it is also called visual target analysis. The fundamental task is that we want to do geological classifications from images. Therefore, multispectral reflectance data from images is used for rock classifications. The camera needs multiple filters like ultraviolet or near-infrared filters. Then also some image processing techniques are used. So if we want this, thus we can extract the rock. So We are using, for example, a horizon filter, then a canny edge detector, and finally a rock detector, so that we then just have the rock and can place it into our classifier. The distance to the objects should be considered, so we want to identify the rocks within distance from up to 20 meters, and then during the data acquisition we should also consider the distance, since if we are too near, then we would have an exponentially increase in extractable informations, and if we are too far away, we are losing high frequency variations due to the reduced resolution. Here is a figure of different reflectances of rocks at different wavelengths. Therefore, it is mandatory to use different filters for rock classifications on our camera. Both images are from the textbook in chapter 12.1. You can see here in this image, for example, that at different wavelengths, the reflectance values are quite different for the different rocks. Now let's move to the classification part. For that, I want to show you, for completeness, a small list of parameters how a rock can be classified. For example, the size, the structure or shape are parameters which are needed to be described beforehand. I assume that you know what Bayes theorem is. If you don't know what Bayes theorem is, please take a look at the video description. There is a video linked which has some nice illustrations of Bayes theorem and explains Bayes theorem in an analytical fashion. However, I'm going to give a short recap on Bayes theorem so that you have a basic idea. The idea is that one has some prior evidence given an hypothesis. With this prior probability, one can calculate the posterior knowledge given some evidence. So, for example, that one has some sensor data given a current state, one can derive some hypothesis. With this probability, one can calculate the probability of a hypothesis given an evidence. For that, also the probability of the hypothesis itself and the probability of the evidence are needed. This formula is Bayes theorem. So we want the probability of a hypothesis given some evidence, while we are having the probability for some evidence given the hypothesis. This was a simple explanation of the formula. I want to mention again that watching the video in the video description is a good opportunity to understand it in a graphical and analytical way. Now let's take a look at some examples of Bayesian classifiers. Within this image you can see a classifier with two root nodes, a dolostone and a basalt. The root nodes are having their prior probability tables with the predefined parameters. The edges are the statistical dependency and can build complex probabilistic models. Thus, the strength of the edges is quantified by conditional probabilities. In a statistical way, one could say that the root node causes the child node. The child node has therefore a conditional dependency on the predecessor nodes. This representation of the dependencies is an essential feature of Bayesian networks. The initial condition, the initial conditional dependent probabilities of a node are then represented in such a prior probability table as I have shown you before. Within this example here, the properties of the rocks are our inputs, and the outputs would be then a probability distribution over all rocks. Therefore, Bayes' theorem is used to determine the conditional probability tables for each node based on its predecessors. Thus, one becomes a causal model of the world with the Bayesian network. The Bayesian network can therefore be modeled as a triplet of three variables. First, the set of our vertices, so these here, then the edges, and also, of course, the probability tables which are in our rocks, in this case here. One could also use dynamic Bayesian networks. Here the idea is that one has two or more time slices. The time slices are consecutive. For that purpose, some white noise is added to the observation vector. However, in the most cases, naive Bayesian networks are used for classification. Then each attribute or attribute node is conditionally independent to the others. You can shortly think about it, what that means for our graph. This, for example, here is a naive Bayesian network, since here the attributes do not have any edges between them. This makes sense within the context of rock classifications. For also, of course, this also would be a naive Bayesian network. And as I mentioned before, if we would have 700 rocks, this would get quite complicated. So now let's summarize the previous set on one slide. So the nodes are our random variables. The edges are the conditional dependency or independency if there does not exist an edge. The output is a probability distribution of the variables. So we are applying Bayes' theorem on complex structures so that we then retrieve a setup of systems of beliefs. The root node comprises a prior probability table. The child node has a conditional dependency on the predecessor nodes. I mentioned before that it is important, and of course also the graph, and it is not allowed that the graph has some circles. So we are having directed acyclic graphs. I also mentioned before that we don't want to fall into a cavity, so that we are try to minimizing the probabilities for false positives, and this is done with weighted filters. So we are assuming a Gaussian or normal distributed world, and then for that purpose we are going to minimizing the probability for false positives. Also, extreme value theory should be considered, which I'm going to explain you on the next slide. So the basic idea of extreme value theory is that we are having our normal distributed world and also taking a look at the tails of our distribution. This means that if we are having an Gaussian world, so something like that, then we are going to take a look here at the tails of our distribution. So to this part and to this part, and are building again our own distribution. So this means that we are now taking here this part, and then we are going to take a look at this tail, for example, here, and then maybe there are some peaks within this tail which we should also consider. So the idea is then that we are now open for some new data which might be interesting. However, in the most cases, of course, we are taking the maximum and are neglecting the other stuff. Now I'd like to show you a small website, and on this website you can play a bit around with Bayesian networks, and yeah, also you can build your own Bayesian network if you're interested in, and this website is of course also linked in the video description. Yeah, so here is a small example of a Bayesian network. Here in this case for animals. And for example, if we're going into the air, it is quite probable that we are having a robin, or if we're going back to land, and yeah, you can play here around with these different parameters and can then play a bit around, and of course you can also build your own Bayesian networks if you're interested in that. It could become quite complicated. So here is an example of an insulin dose adjustment, and yeah, you can imagine that setting this conditional dependencies up by hand can become quite complicated, which brings us to our next point in my talk, which is setting up the network structure if we don't have any knowledge about the conditional dependencies. If we don't know the direct dependencies between the edges, the setup of the network structure is not such easy. The idea is that we are using a dataset where we have some measurements which are associated with some features. Then the measurements are used to update the probabilities for each node. So the idea is that we are finding a maximum in our a posteriori beliefs. This is also called MAP, which stands for maximum a posteriori. It is an extension of the maximum likelihood. The extension is by introducing the prior probability with Bayes' theorem. The simplest prior distribution is a Gaussian distribution and is often used. So the idea is that one tries to maximize the likelihood. The likelihood can be seen as the gain of the data D one wants to maximize. Therefore, in the most cases, we've got some logarithmic term in our maximization formulas. The scoring function measures then how good our current network structure is working with the given data set. An example formula could be the following. Here D is our data set and P of x, given their conditional dependence on their predecessor node, is in our sum which we want to maximize. This maximization process could also be done by some approximation functions for simplifying this problem. However, one should consider overfitting, since if one adds the edges and their conditional probabilities till the network seems to be perfect, one has the problem that then the classifier won't perform good on new datasets. So, setting up the network structure is not easy and becomes NP-hard when the number of variables increases. One approach to counteract on this problem is done by limiting the number of parent nodes for each child node. However, this cannot be suitable for our classification. If the Bayesian network is not accurate enough, for example due to too complex network structures, one could also chain Bayesian networks one after each other. Also, it is possible to start with setting up the network structure by adding edge after edge. So, First, one just has the nodes without any edges. With this approach, or with these approaches, the problem is in the first place not too complex. Now I'd like to show you a small example from the textbook, which is the Nomad rover. The Nomad rover is a test rover, or was a test rover in 1917 from NASA, and it was used in Antarctica, and they used the rover to test a Bayesian network for dark meteorite detection on ice. It had 3 layers: a control layer for sensors and actuators, a sequencing layer for coordination of primitive behaviors, and then finally a planning layer for optimizing mission parameters as energy consumptions, for example. It had 2 modes, an acquisition and an identification mode, and here you can see again that we first have this acquisition and finding of new data, and then the identification and classification. If then a science alarm was triggered, after some segmentation, the first Bayesian network was triggered. Bayes theorem, the Bayes network had some prior expert knowledge base, which simply means that we are having this prior parameter table, which needs to be set up by some expert. Nomad could differ between 42 samples from infrared spectrometers, and if we compare this to the tasks Perseverance is solving today, this seems rather simple, since we are here talking about rocks on ice, and we're not having any dust. So we can see here the gap of more than 20 years between those rovers. Quite good, I think. Now I would like to summarize the previous learned. So rock classification is done with cameras with different filters, like near-infrared or ultraviolet filters. The classification is based on feature lists which need to be set up beforehand, and every root node has its own feature list. These feature lists, of course, need to be set up by some geological expert within the context of rock classification. Bayesian networks are acyclic directed graphs and are used for classification, and of course are working for classification. A child node has a conditional dependency on the predecessor node, so a conditional dependency on their parent. Outlier removing is done with weighted filters against false positives. So we're assuming that we are having a normal distributed world. Extreme value theory should be considered on the other hand, so that we are taking a look at the tails of our distributions for finding possible new interesting data. Also, the setting up of a network structure, if we are not able to know the dependencies between the nodes, becomes NP hard. This can be counteracted by adding edge by edge, so that we are first having only our nodes and then adding one edge after edge. Also, one could chain Bayesian networks, and finally, in the rock classification context, one could also assume that the attributes are independent of each other. With that, I would like to come to an end of this talk, and since this is a pre-recorded video, feel free to write me an email, since you cannot ask me any questions directly. This video was a basic overview about Bayesian networks and how they are used in yeah, autonomous systems and of course in planetary exploration systems. And if you want to dive into the math, you should take a look here at our textbook and these given literature. With that, you can derive the mathematical explanations in a quite good fashion. So, thank you and bye bye.